everybody. My name is Islam. This is my work to contribute to 38th EGMRS International Conference on Material Science. It's based on Rudolph's power phase, abbreviated Lansana Nicolate, dubbed by samarium ant as a stunning electrocatalyst for oxygen evolution reaction. Here are the main outlines related to the energy challenges by hydrogen, the electrochemical water splitting, and perovskite, and special phase of perovskite, which is Rudolph's bubble, and experimental work, results, and discussion. So the aim of this work is to produce an innovative electrocatalyst based on Rudolph's bubble phase for oxygen evolution reaction. This is a greenhouse effect. Actually, Earth cannot re-emit effectively the heat into the space. That's why the temperature of the Earth is increasing. This is a literature study about the atmospheric carbon dioxide and the Earth's semi-freeze temperature over the last 140 years. The increasing of CO2 ratio was actually effectively increasing the temperature of the surface. That's why we seek to resolve the energy problem, because it's the main contributor to the greenhouse emissions. These are the energy resources, the renewable against the finite sources, and the contribution of each one in terawatts per year. And you can see how much amount the finite contribute versus the renewable. These are the types of renewable and energies, and we actually are going to focus on hydrogen production. So why hydrogen? Hydrogen has high energy density, can be easily transported, and also no CO2 emissions, and this is actually related to the production method, and its safety and versatility. So there are more than 3 types actually of hydrogen based on the production method. There is gray hydrogen, blue hydrogen, and green hydrogen. Actually, green hydrogen is the more effective one because blue and gray are actually contaminated by CO2, so they need some purification processes, and also they contribute to the gas emissions. Actually, hydrogen production can be carried out by electricity and by photons. The state of art of this electrocatalysis is related to the precious metals like rubidium oxide, iridium oxide for oxygen evolution reaction, and the platinum-based materials for hydrogen evolution reaction. These precious metals actually suffer from high cost, scarcity, and low biofunctionality. The material we have used is actually perovskite. So perovskite was first discovered by perovskite as a Russian scientist. He actually discovered calcium titanate, and it was formula discovered was ABX3, where A is a cation, B is a cation, and X is an anion. For perovskite, we are going to use a special phase which is named Rudolph's bubble phase. Actually, this is the main. This is the main formula of perovskite: A of N, B of N, X of 3N. And this is Rudolph's bubble phase. Actually, A of N plus 1, B of N, X of 3N plus 1. So there is an extra AX layer, which is called salt layer. We can see this. This is the rock salt layer. So what was our work? We actually have prepared Lansana nicolate and also doped it using samarium instead of Lansana by using 0.1, 0.2, 0.3 ratios. This was a schematic diagram of our work. Actually, our method of preparation was based on citric acid combustion technique. We actually use nitrate precursors of this metal, and followed by standard method like magnetic stirring, zinc calcination, and grinding. For our electrode preparation, we have used drop casting method as an effective method of this work, which is not as simple and easy. So what you have got from this work, actually you have prepared the pure phase of rhodopsin power phase, but it was very low, contaminated by some ratios of nickel oxides that actually didn't react. And this is obvious in this peak here. And this is the 100% peak actually change with samarium doping. There was a broadening and shifting to higher 2 theta. These are some parameters of XRD, like the main unit cell parameters and theoretical density, crystal size based on the pi and Williamson Hall, and the microstrain and dislocation densities. This was the micrographs of our work, and it was actually tending to be micrographs connected to each other or stacked over each other, which supported the Lawson power phase and perovskites. So our results in the electrochemical application are based on the performance of OER. We have carried out linear sweep voltammetry and Tafel slope and chronopotentiometry. Actually, we have got a high current density in this work, and the optimized sample based on this application was lanthanum nickelate doped by 0.2 samarium. And to check the mechanistic reactions, we have carried out kinetic reaction. We have carried out Tafel slope, and the lowest value, which means the best, was also related to 0.2 samarium doping. So we have carried out the chronopotentiometry, which is IT curve for 24 hours to produce 10 milliamperes per centimeter square as a current density. To check the electrochemical active surface area, we have carried out different cycle voltammetry with different scan rate. This is the electrochemical surface area we have got. The optimized sample was got the highest electrochemical surface area. And this is Nyquist close before and after 24 hours, which supports the high stability of this work to produce 10 milliamperes. These are the equivalent circuit, was actually the best for the optimized sample, which is 0.2 samarium doped. Samarium hydrogen is a very important resource to resolve the energy problems, and water splitting is a good way to form to produce green hydrogen. Perovskites are good candidate for electrochemical, especially reverse bubble phase. These are the references. I want to thank Professor Chang from National Taiwan Ocean University, and also to thank Professor Louis Castot from Paris-Saclay, and my supervisors from Venezuela University. This is my scopes profile. Thank you.
Thank you, Islam, to be in time. I have 2 questions.
Thank you for your presentation. It's very interesting that you work in perovskite. Did you measure band gap of your material? This is a first question. The second question: why we see them in your XRD? You see some shift. Why this shift?
For the first question, actually I have used this material for electrocatalysis, not photoelectrocatalysis. In photoelectrocatalysis, we tend to measure the band gap because here we are using photo to induce this electron hole pair production, so there's no need to measure it here. I have measured it in previous works, but not in this work actually. Your second question, this actually is a compound, not a nanocomposite. So it's normal to find a deviation and shifting in the peaks and the change of all the XRD parameters we have measured. This is a normal thing to occur. It's not normal to add some some ions like samarium ions inside a compound actually without changing the XRD, in the mean XRD. So
because if you have a network of perovskite, you just remove one atom from
no, it's actually.
I think there is no diffraction, that shift will be shifted.
Actually, this is lanthanum nickel, the main count, and this is actually the doped samarium. So we have checked this peak, the main peak, which is 100%. We're actually confirming the parts over this. So there was some broadening and some shifting. This is related to the new ion we have added or we have doped our sample, it may be smaller, so it will cause some shrinkage in the lattice unit cell, or if it was larger, it will, you know. So that's why this spacing are going to change and all this peaks so on.
Thank you, Islam, for the presentations. Any other questions? Good talk.
Maybe try your system with pure water or wastewater for production of iron.
No, this is 1 molar KOH. Actually, it's pure water.
Pure water.
Pure water.
You don't have any plan to apply wastewater?
Actually, my first work on perovskite was in my master, and actually I have just prepared for one, which was lanthanum cobalt ferrite. This is my new work in reducing bubble phase as a starting phase from perovskite. Actually, I have prepared several phases, but I didn't check them all yet, so this will be one of my.
Okay. All the best.
Sorry, Islam. There was a question? Okay.
Thank you very much. So our next speaker is محمد. He will be talking about zinc.